Hello, I'm Andrew Purvis. I'm the General Manager for Europe, the Middle East and Africa with the Global CCS Institute. I would like to welcome you to our webinar today, which is one of a series of webinars which the Global CCS Institute is running. We have attendees today from all around the world. Today's webinar, how to manage technical risk in CO2 capture technology development. Scaling up, integrating and optimizing CO2 capture plants certainly can be associated with high risk and high cost, and currently there is a lack of standard codes and procedures to be used. This makes the development of CCS projects challenging. In today's webinar, DNV GL will present their recommended qualification procedure for scaling up CO2 capture technologies from the lab to commercial scale. The technical risks associated with new CO2 capture technologies can be managed through a systematic qualification process. This process focuses on the identification of the risks and indicates how they can be evaluated and reduced with adequate qualification methods such as analyses and testing. Aker Solutions today will illustrate how this procedure has been applied for scaling up their proprietary CO2 capture technology. I'd like to just cover a few housekeeping matters before we start. Today's webinar will be recorded and will be made available on the Institute's website along with the slides used in the next few days. Now, let me kick off by introducing you to our presenters, Anastasia, Isaenko and Oskar Graff. Oskar Graff is the Chief Technology Officer from the Department of Clean Carbon from Aker Solutions. Oskar was educated at the Norwegian University of Science and Technology, from which he was granted a Master of Science in Chemical Engineering. He's been with Aker since 1980 and has had a broad career, been involved in concept and technology development, major offshore and onshore projects, and also has worked in different management positions. Oskar's been involved in CO2 capture technology since 1999, and he assumed his current position as Chief Technology Officer in Aker Clean Carbon Technologies in 2008. He's currently Department Manager and CTO for Carbon Capture in Aker Solutions. Our second presenter will be Anastasia Isaenko. Anastasia is a consultant, carbon capture and storage with DNV GL. She was educated in process engineering and has worked in the carbon capture and storage area since 2007. Anastasia has been involved in technology qualification projects within CCS and renewable energies, as well as the development of DNV recommended practices for qualifying CO2 capture technologies. And my final housekeeping point is around questions. All attendees are welcome to submit questions throughout the presentation through the Questions tab, which will be on the GoToWebinar control panel, which should be visible on your screen. Questions will be moderated and posed at the end of the presentation, but please feel free to submit questions as they occur to you as we go through the presentation. We will do our best to get through as many questions as we can today, but please be aware we might not be able to answer everything. However, I'll do my best to get through as many questions as possible. The webinar will be recorded and will be available on our website in the next few days. And now, without further ado, let me hand over to Oskar Graff, who will commence today's webinar presentation.
Hello everyone, it's Oskar here, and I will give a presentation which sums up our technology activities and test program in order to reduce technical risk related to our technology. First, a summary of our activities. We have been working with CCS in Aker for more than 20 years. And we have an extensive R&D program ongoing to test certain issues related to our post-combustion technology. And we also have our own test facility, a mobile test unit operating, which I will come back to. And in our company we are about 30 experts on flue gas handling and post-combustion technology. And in Aker we have followed this step-by-step approach in order to handle risk. And we started early in 1996 with a small pilot in Trondheim at the university there. And then we did all the conceptual work and design and delivered the Sleipner platform for CO2 handling. And later in 98 we established a larger pilot working on a gas motor. And then in 2007 and 2008 we established a dedicated company for carbon capture, and the mobile test unit, as you can see, was started in 2008. And now we are testing our technology at Mongstad, the technology center in Norway. Regarding risk element in the carbon capture technology, it's mainly two areas for concern. It's during the construction period, and that is very much related to integration with the emitter, the existing plant, where we are going to capture the CO2 from, which could be challenging. And of course it's related to the operation of the capture plant when it's ready. And I try to list it all kind of elements which can go wrong and which we have to focus on as a technology supplier. And of course we deliver a complete design of the carbon capture plant with all the utility requirements. And then we have to find a good integration with the main plant. It's physical connections on the flue gas, but also maybe sharing on utilities and using common utilities in the plant. Heat and mass balance is of course very important, and the steam demand we need for using the post-combustion system. Material selection is very important and is very much related to flue gas and to the solvent in use. Instrument control, they should be working so we have control over the plant. Equipment, there could be details in the equipment. We have seen gaskets, for example, in some equipment could fail. So it's not only the main equipment, but it could go into the details. And so I mentioned solvent. We have screened over 80 different cocktails for carbon capture. And they behave differently also in respect to the materials. Turndown is normally a discussion between the owner of the plant and also the technology supplier, what kind of turndown you can offer. Availability is important. How much CO2 can you deliver over the year? Lifetime, it's normally 25 to 30 years. CO2 purity, it's very much dependent on what is the use of the CO2. Normally it's going to storage in geological formation, but if you use it for other purposes in food, there could be different specification for the purity. Liquid waste is what we get out of the amine systems, and it's normally burned in special treatment plant. Emission to air has been focus at least here in Norway for the last years, And it's very important to have control of what you emit out in the air after you have treated the flue gas. Carbon capture rate could vary from plant to plant. It's normally 85 to 90%. Of course, you can go to 99 if you want, but then you get the energy penalty. And solvent makeup, how often do you have to adjust solvent during operation is also important. And to really understand the plant and to give performance guarantees, you have to verify the technology and do tests actually before you can give any process guarantee. So that is very important from a technology supplier point of view. And then if you look at the main challenges in the carbon capture plant, we see that it's very much related to the amine solvents. And most of the technology companies are looking for improved solvents, and they have different behavior. With respect to capture efficiency, energy demand, and especially degradation is very important if you have a challenging flue gas. So then you need a very robust solvent. And again, corrosion is very much related again to degradation and flue gas. And we have also seen foaming in some system and some operation of the plant. And reclaiming is kind of washing machine where you take out impurities from the main solvent loop and you take it out as waste. And emission to air is also very much related to flue gas and the type of solvent you have. And of course, the HSE data for the solvent is also very important. What kind of solvent are you using and what kind of effect does it have to the environment or to human? And materials we have seen is very important, and we do test on different types of materials, and the best way to test it is actually in a real plant with real flue gas. And we have seen typical corrosion in some materials, and we have also had challenges with some gaskets. They look almost the same, but there are slightly different way of making these gaskets, and some of them could fail. Equipment type is also important. All the details in the equipment should be working perfectly for 30 years, or at least you know what to replace. And I would like to highlight this actual flue gas condition, that you need actually to test on the real flue gas before you can make a commercial offer. Because the coal flue gas, for example, from a coal-fired power station is not the same. It's very much dependent on the coal and how you treat the flue gas at the actual plant. And one of the biggest issues in risk element has been the scale-up. And there's been a long discussion how many times can you scale up before you enter into very high risk. And I will come back to that. But what is highlighted there is you can only do a commercial offer if you have been testing for at least 6 to 12 months on the actual flue gas in a large scale pilot. This sums up our R&D activities, and it's quite substantial. And what we learned from all these activities, it's mainly to have a better understanding of the process and to eliminate risk. And we have used DNV recommended practice since we started up our development. And we have followed the procedures since the early start of testing, and via all the scale-up we have been through. So the beauty with this DNV procedure is it's a systematic way to treat risk, and we identified risk element, and then during the testing and checking out, we reduce the risk, and it's kind of housekeeping. We can follow how we manage risk, and at the end we have very few risk elements left before we enter into full scale. And I would like to mention the CCM project and the technology qualifications. It was about 2 years activity here in Norway. It's based on the same DNV procedure, and there we identified 50 risk elements before we started up. And after 2 years, we have eliminated 48 of them. And we ended up only with 2, and that was related to foam and to compression. And the compression part was actually related to information from compressor supplier. So the 2 remaining elements there were not regarded as high risk for us. And we have a lot of test facilities around, and we have several pilots in operation. And as you can see in the down right corner, we have also tested in Spain emissions to air to get a better understanding. The Solid R&D program has been going on for 6 years, and we finalize that next year. It's a step-by-step testing of solvent together with Sintef in Trondheim. And you see we start with a lab bench scale, and then we do pilot scaling. And then we have a full height pilot test rig in Trondheim where we do the final screening before it enter into what we call industrial environment, where we use a mobile test unit. And you can see also a picture from Heilbronn in Germany, where we have cooperation with ENBW. And finally, the best candidates from these tests enter into Technology Center Mongstad, where we are operating the main plant now. The mobile test units, it's container-based, it's easy to move around, and it's a complete carbon capture plant that has been in operation since 2008. It's very easy to modify, and it's used to verify our performance of the process. We use different solvents, and we can test materials in the plant. This is just a summary of the MTU activities. It's been around in UK, Scotland, and in Alabama, US, and 2 different locations in Norway since 2008. And we have different test results from coal-fired power station, gas power station, and at the moment we are testing on the cement factory here in Norway. As you can see on this slide, we started up 1st of May, and we are now testing for the first time on the cement industry. And the cement industry contributes about 5 to 6% of the CO2 emission globally, and the CO2 concentration is up to about 20%, so it's high. So it's a kind of low-hanging fruit. So, but again, it's a different flue gas, different behavior, so it's very important to test on the actual flue gas. Just a summary of the plant at Mongstad. As you can see there, it's quite unique and flexible. 2 different flue gas sources, a gas power plant and a cracker, large turndowns, 2 different strippers for alternative flue gases. And we also, you can see here, we have the mobile test unit running in parallel. Extensive monitoring in the columns, and there are different beds in the columns, so we can test different heights. And it's quite unique also. It's a concrete absorber with a PP liner, and we also have introduced this energy saver, which could reduce the steam consumption about 20%. So it's very flexible and it's unique. Here you see a picture of it. Here you see the stripper column, and you see the absorber here, and you can see the mobile test unit operating in parallel. To sum up from Aker Solutions' point of view, going from lab to commercial plants, we are doing a lot of tests in order to reduce the risk, and we have followed the procedure from DNV. And since 1996, we have tested on 6 different pilots, including the final step, which is the Technology Center Mongstad. As you can see from the scale up here, from the mobile test unit to Technology Center Mongstad, it's a scale up of about 50, which is pretty high. And then going from Technology Center Mongstad to full scale, it's about 15 times scale up. So the main risk is now taking out by testing at TCM. So that concludes my presentation, and I'll leave the word to Anastasia.
Okay, thank you, Oscar. And now I'm going to talk about the procedure that helps to manage technical risks in CO2 capture technology. In DNV GL, we call it technology qualification, and Oscar has already referred to that several times. Our definition of qualification is that qualification is the process of providing the evidence that the technology will function within specific limits with an acceptable level of confidence. And our technology qualification process helps to increase the confidence in the CO2 capture technology among different stakeholders. Oscar has already mentioned several challenges associated with CO2 capture technologies, and probably the biggest one is the scale-up. Also, there are challenges related to the equipment and materials, integration of the CO2 capture plant with the emitter. But basically, introducing new and proven technology at the commercial scale represents technical risks for different stakeholders. And those risks can be related to the technology performance or to project costs, overruns, delays, also to HSE issues. And many technology providers are unable to give process guarantees on some key performance parameters. So DNV has came up with the recommended practice, DNV RP J201, which is called Qualification Procedure for CO2 Capture Technology. It was issued in 2010. And now I'm going to walk you through the steps of that qualification process. Here on the left you can see the DNV RP that I referred to earlier. And on the right here you can see the steps that the developer have to go through in order to qualify our technology. You can see here that the process is iterative, so it is possible to go back to the beginning and probably to make some modifications in order to make sure that the technology will be successful in the end. And the first process is qualification basis, development of the qualification basis. Here, the developer defines, for example, the boundary conditions of the technology, and also defines the expectations to the technology. For example, capture rate, emissions, energy penalty, reliability, and so on. So this is where the whole process starts. After that, the next step is technology assessment. That is where the technology is divided into manageable elements, and these elements are rated in terms of novelty. You can see here the schematics, how we normally do that. What we mean here is, for example, if you have a pump, and this is definitely proven technology, you would put it here probably, it is proven. But if you introduce it to the new environment, like if you put it subsea or introduce new liquid, then you will probably get it here, and that makes this element novel. So after this step, we have a list of novel technology elements, which we take to the next step, which is threat assessment. In this step, we identify all relevant threats related to these novel technology elements that we have identified in the previous step. And for all these threats, we try to identify associated risks. So here we would come up with the risk ranked high, medium, and low. And in the next step, we would take only the threats that would lie into the medium and high fields. And the next step here is development of qualification plan. As I mentioned, we focus here only on the risks that are of high and medium level. And for those threats, we identify qualification activities that can help reduce, to bring those threats to the low risk level. The next step is the execution of the plan, and here we perform all those qualification activities that we identified one step above, and this is probably the most expensive and time-consuming step. And in the end, the last step, here we have to confirm that the functional requirements that were laid down in the qualification basis in the first step of the qualification process are actually met, and the technology the technology will be successfully. Through our qualification process, we also have some deliverables from DNV GL side, and there are 3 of them. They are reports and statement certificates. And the first one is right after the technology assessment. We produce technology assessment report and statement of feasibility, and that statement shows that there are no showstoppers to the technology. The next deliverable will be technology qualification plan and endorsement of qualification plan. And that certificate states that technology is executable. And you see, we issue this certificate right before the execution of the plan, right before the most expensive and time-consuming part is coming. And the last report is technology qualification report and technology certificate. That one states that technology is qualified. So to sum up my presentation, as I mentioned in the beginning, the risks of introducing unproven technologies can be high. And DNV GL's methodology focuses on addressing high-risk elements. This is very important because here we can optimize the cost involved in the development of the technology, because here we focus only on the high-risk elements of the technology. Also, the methodology ensures that adequate tests are undertaken so that each test addresses the risk that we have identified. And the technology risk management builds confidence in new technologies. So that brings me to the end of my presentation.
Okay, thank you, Anastasia, and Oscar, for your presentation. We've received a number of questions through the webinar, which we'd like to start to address now in the time we have left. So maybe I'll start by asking, how do you go around creating a qualification plan?
So the qualification plan, as I mentioned, we we focus only on the high-risk elements and address those risk elements in our qualification plan. And those we address it with the help of tests, or so we assign different qualification methods to the high-risk elements, to threats that we have identified through the process. And those qualification methods can be tests, it can be modeling, or just modification of some procedures that would help to improve the performance of the technologies. And that combination helps to optimize the costs, so you don't have to pay only for the tests, which are normally very expensive. We're trying to find our way around and suggest other qualification methods as well.
Okay. What are the remaining risk elements for a full-scale application?
Maybe it's Austria, maybe I could answer that one. As you know, a lot of testing has been carried out around the world on carbon capture with different technologies, and I would say that several technologies are now available for full-scale application. For ourselves, we have a dedicated mobile test unit, which we now have demonstrated that we have control on the scale-up by designing the Technology Center Mongstad, and we have verified Technology Center Mongstad versus the mobile test unit. So now we can use the mobile test unit to test on actual flue gases, on cement, and on different type of flue gases. And by verifying the results from these tests, we are able to offer full-scale design based on these tests. But I think there are several technologies now available for large-scale applications. And most of the large risk elements have been removed over the last 5 years.
Okay, thank you. Can you perhaps give an example of a test done to reduce risks related to emissions?
We have done several tests. In Alabama, we were testing on coal, and we saw that we got some mist problem. It's kind of fog generation that actually goes through the absorber, and part of the liquid amines and the water will follow the treated flue gas to air, and that will give an increase in the amine losses. So it's very important to control the mist system, and we developed the mist system, anti-mist system, that were able to reduce the emissions to acceptable levels. And we have also developed what we call the anti-emission system, which is a more chemical treatment system of emission as a kind of final polishing step in the absorber, which eliminates almost every amine losses to air. So by doing all these tests, we are able to verify the emission level for different type of flue gases.
Okay. Is the technical qualification certificate issued for each piece of equipment, or is it for the overall technology package?
That is issued for the technology package. Yes, it is for the technology.
Okay. In the presentation, you emphasized that testing on actual flue gas is very important. Are there specific elements or components in the flue gas that you'd be most worried about?
Yeah, it's definitely not the CO2. It's all the other impurities which you may see in the flue gas, and that very much different on the type of fuel you have, what type of coal do you have, and what type of natural gas do you have. Do you have any sulfur in the natural gas, for example, and how is it treated? And the same applies also on the coal-fired power station. What kind of flue gas treatment do you have before you enter into the carbon capture plant? And we might put up some extra pre-treatment depending on the type of power plant we are seeing. So from plant to plant, flue gas may vary, and you can get a lot of surprises if you don't have control on all the ingredients in the flue gas. And it's particular if you have SO3, for example, you can get the mist, and for some plants you can have catalysts following dusts from coal-fired power stations. You have fly ashes. So it's a lot of impurities that can affect the post-combustion system, which is a kind of large-scale washing system, cleanup system for the flue gas, and the impurities can then be accumulated in the amine system and can generate degradation, corrosion, and a lot of operating problems. Foaming, for example. So it's very important to really understand the flue gas and have control of the operating parameters.
Thank you. Have potential future operators of full-scale CCS plants recognized this certification as adequate for the requirements? If so, are you able to say how many or who they might be?
Yes, we have Gas Nova. We have done. Gas Nova has used our procedure for the potential suppliers for the CCM capture plant. So several developers has gone through, 5 developers have gone through our qualification process, and Aker Solutions is one of them.
Okay. Does your, how does your recommended practice differ from other engineering good practice guides for scale-up, for example, those used in the chemical industry?
I'm not sure. I'm not sure I'm familiar with any other procedures like that. I know that our procedure was adopted by Statoil, for example. They are following the same qualification procedure for the oil and gas field developments.
Okay. In terms of the design process, when is the proper, what's the proper timing to deploy the qualification process? Is it in the design stage or after the technology is installed?
Yes, absolutely. It's better to introduce this qualification process the earlier the better during the design stage.
Do you see a 6 to 12 month test as being sufficient to predict degradation and corrosion long term in the solvent system?
Yeah, I would say that that is kind of minimum requirements, and we have had a lot of discussions on what will happen after 5-6 years, and it's hard to conclude that we will use the same solvent after 10 years, but it could be replaced at some time. But we know now with our technology that we can run it for several years, and I think that will be sufficient for the client to have control over the solvent cost and also the operation of the plant. But we have seen that many on an early stage test, they see that the solvent behave very well, and they think that this will last for the remaining test period, but suddenly we see the degradation accelerates, and it's very much related to accumulation of impurities in the solvent. So it's a kind of acceleration of the degradation and corrosion in the system. So you really have to system over several months, and we would recommend to at least test for 6 to 12 months before you enter into a commercial deal on the solvent.
Thank you. Have you applied the qualification procedure to other technologies than post-combustion CCS?
Yes, we have applied that to the oxy-fuel combustion technology as well.
Okay. Can the DNV recommended practice be applied to wider risks around a CCS project that's beyond the technical risks? And how has Aker in particular found integrating the technical risk work with wider risk management processes?
I think it can be, at least the methodology can definitely be applied to identification more than technical risks. So like risk related to the cost overruns, as I mentioned, and project delays, those risks can be identified through this process as well.
But it's also important to remember that the carbon capture plant in itself, it's just one element in the CCS value chain. So you must have control over the main plant and the integration with the carbon capture plant, and also the transport and the storage part. So all these elements you have to have a full understanding of and control the risk in the whole value chain. So I think that's also a very important aspect to keep in mind. But we have found that the DNV methodology has been good because it's a systematic way of identifying potential risk elements and to put up a plan for how to check those risk elements and to clarify them. So it's a systematic tool which is good for process engineers to use, and also mechanical engineers to really have a full understanding of the technology risk.
How many CCS technologies have been qualified by the DNV procedure so far?
No, we don't really know.
Okay. The consequences of risk, is that also estimated in terms of additional costs in the DNV procedure?
Let me check. Could you say it again?
So the consequences of a risk, is that also estimated in terms of additional costs in the DNV procedure?
Yes, yes, definitely. It is.
For which process parameters of CO2 capture plants can performance guarantees be given?
Well, that's a very general question, and I very frequently get that question. And you know, I think people should be a bit careful with putting too much performance guarantees, because then you can get over-design and add cost to the carbon capture plant. And I think it's very important to try to reduce the cost of carbon capture. We know that it's hard to get the market going due to the high cost of carbon capture plants, and I would say it's more important to get down the cost and maybe be a bit reluctant on some of the process guarantees in order to apply the technology in order to reduce the CO2 emission and global warming. That is more important than actually to meet a figure. But most of these parameters you have control on after doing tests. So you can show to the client that you have done tests, and you can demonstrate, for example, a carbon capture rate of 93% or 90%, or you can also demonstrate your steam demand. And you can demonstrate your makeup requirements and waste generations, and also the emissions to air you can demonstrate the values for. But normally when you give process guarantees, it's contractually connected to some penalties, and of course it's not very difficult to give performance guarantees if you don't have any penalties. So it's also kind of level of penalty you are seeing. So I think it has to be a balance between the performance guarantees you give and also the penalties. But I think the client or buyer of carbon capture should discuss this with the technology suppliers and try to establish a sound level of process guarantees in discussion with the technology suppliers.
Thank you. Was the DNV recommended practice used during the design of the full-scale Mongstad carbon capture project?
Well, several technology developers have gone through the qualification procedure for the full-scale Monster project, and Aker was one of them. So yeah, Gasnova was using our qualification procedure for that.
Okay. And how long does it normally take to run a qualification process for a capture technology?
Well, it depends on the tests in the end, but the first several steps up to the execution of the qualification plan can take, I don't know, a month. It depends on the complexity of the technology and how fast you're able to mobilize everyone to perform that. But then the tests, it can take, we don't know. Yeah, it's up to Aker is still testing.
Yeah, we are saying that at 6 to 12 months you should actually test in a larger scale pilot before you enter into full scale.
Yeah.
Okay. From your experience, which of the CCS technologies that you've evaluated has the lowest level of technical risk?
Yes, Aker. But it's, it's impossible to answer the question.
Okay.
Could you? I think if you look at what has been going on, it's a lot of tests on post-combustion. So you will see there are a lot of test reports on post-combustion, and there are less demonstration on other technologies. So we from Aker, that's why we have put our main focus on post-combustion. That could be an early market mover. So we believe that it's less risk related to post-combustion.
Thank you. Can the procedure be applied to single pieces of equipment?
Yes, definitely it can be. But then again, those pieces of equipment will be broken down into these manageable elements, and also the threats will be identified for each of those novel elements. It is possible it will be just a smaller kind of scale of qualification.
One good example is the absorber, which we have spent a lot of time together with DNV on. And that is, if you look at the absorber footprint, it could be from 100 to 300 square meters. So it's a large piece of equipment, and it could be 50, 60 meter high. And to really control the flow through the absorber when the gas flows upwards and the liquid flows downwards, to actually have a good control on the contact surface between the liquid and the gas, so you don't get weeping or flooding or foaming, whatever you can get in an absorber. That is a very important issue. And frequently we have discussed with the client, when do we split up in parallel? When is the units too big? Then you have to split into 2 units. So that's a kind of example on what we are looking into.
Thank you. I'm sorry we weren't able to get through all of the questions that we had sent to us in the allowed time. I'm going to draw things to a close now by thanking Anastasia and Oskar for their time in sharing their expertise with us today. If you do have any questions, you can continue to submit those to the Institute through our webinar inbox, which is webinar@globalccsinstitute.com. Just as a quick reminder, the webinar today has been recorded and will be made available on the Institute's website in the next few days, along with all the slides that we used. Finally, as you are leaving the session today, we've put together a very quick 3-question survey, and we'd really appreciate it if you could take the time to complete the survey to help us improve our webinar program. I certainly hope you found the webinar today valuable, and once again thank you to Oskar Graff and Anastasia Isaenko for presenting today. Thank you everybody for your attendance, and goodbye.